Hey everyone and welcome back to my channel. So today we will solve the most important questions on op-amps. So this will be a series. So we will do most important questions on op-amp, MOSFETs, and already we have done it from diodes and from switch capacitors. So you can go and check out those videos. So we'll continue those we'll continue a series basically. So today we'll do on op-amps. Okay. So this will be the part 1. So I will just show you the questions at the starting and try by yourself and then mark yourself, right, how many you got correct. If out of the we'll have 4 questions, out of the each question will have 2 marks and negative mark you take as 1 marks. Okay, if you got it wrong you subtract 1, if you got it correct you add 2. Okay, and write down in the comments below how much marks were you able to accumulate. So this one is the first question. You can take a screenshot and solve all these questions, right? Third, and this one is the fourth question. So if you haven't already watched the other videos, you go back and watch those videos. So from there, like we are continuing this series basically. So we'll start with this question. So here we have to determine the V out, that is output voltage in volts, if the V in, that is this particular voltage source, is 1 volts. So whenever you see op-amp, your first instinct comes is just apply the VGC concept and just proceed, right? And most cases it will work. In gate examination also it will work, but if just be careful, if the saturation voltages are given, then you have to be careful that whether it is a positive feedback or a negative feedback. So if you are in an interview or if you are solving the question in gate, then you should check that thing. Okay, if saturation voltages are not given, obviously it has to be negative feedback, but still it's a good practice to check. Okay, so here if I just wanted to check whether this op-amp is in positive or negative feedback, how will I check? I will break this loop, right? Okay, I will break this loop. So if I break this particular loop, then if I increase this voltage delta V, then I'll just show you. Just copy this circuit, take it to the next page. If I just increase this voltage, if I just break this loop, okay, I have broken this loop. Now if I have increased the voltage delta V. So if this voltage delta V has been increased, so overall this is like a voltage divider, right? If this is like a voltage divider, this voltage also will increase, this node voltage also will increase. Now if this node voltage is increased and this node voltage is fixed, so obviously what will happen? This is a op-amp, so overall the output will reduce because V out is equals to AD into V plus V minus. So this is increased, so obviously overall output will reduce. Now if this is reducing, that means this potential has reduced. Now obviously the positive terminal potential has reduced. That means what? Again AD into V plus minus V minus. So obviously it is telling it to lower the voltage, output voltage. But what happened? I actually increased the output voltage, but it automatically reduces the voltage. So basically it is like a negative feedback. So yes, this op-amp is in negative feedback. Same analysis you can do for the second op-amp as well. Okay, so now I will just directly solve. It's just a simple like circuit network analysis exercise. So we can simply solve this thing. What you have to do, as both op-amps are in negative feedback, VGC will be applied. So if VGC is applied, that means that if this potential is V, okay, this potential will also be V and this potential will also be V. So this potential is V, that much is known to us. This potential is V. Now what we can do is, this current is 0, right? Here no current will flow. Okay, so with what things can we do basically here? And no current will flow through here as well. This is 2 volts, this also will be 2 volts, correct, as VGC is applied. So this is 2 volts, right? So from here we can find out a relationship between V and V in. Okay, so what kind of relationship? First of all, I will write a KCL at this particular node. If I write a KCL at this particular node, what will I get? I will get, this is 2 minus, just hold on, 2 minus, this node voltage is 2, right? This is not 2V actually, this is just 2 volts. So 2 minus VO divide by 1 plus 2 by minus 0 divided by 1. All these are in kilo, right? All these are in kilo, and plus 2 minus V divided by 3 equals to 0. So this is the first equation basically. And what is the second equation? Second equation is this. If I apply a KCL here, what will I get if I apply KCL here? I know this current is 2 milliampere. So this 6 kilo ohm of resistance is redundant actually, because here 2 milliamp of current will anyways flow, right? So I can again, this is the KCL 1 and this is the KCL 2. So if I apply a KCL 2 at this particular node, it will be V minus Vi divided by 3 plus, remember if I divide by kilo, right, it automatically converts into milliampere. So this I can directly write that 2 milliamperes of current is leaving. So it is my sign convention. You can choose your own sign convention. So 2 milliampere of current is leaving basically. So that's a simple KCL. That's it. That is a KCL. So from here I can actually replace my V in terms of Vi. So my V will be equals to, this will be minus 6 Vi minus 6. Okay, this will be your V basically. So now if you want to replace your V here in this equation, right, what will you get? Yeah, it will go minus 6. So if I multiply everything by 3, this will be 6 minus 3 V naught, 6 minus 3 V naught plus 6 plus 2 minus of V naught, so minus Vi, and plus 6 equals to 0. So what do you get? So basically you get your V naught something like this. Your V naught will be, you have on one side you have 3 V naught, and another side you have 6, 6, 12, 14, 20. 20 minus Vi. So this value will come out to be V naught equals to 19 divided by 3. So it will be 6.33 volts. Now let's move on to the next question. So this question is again a very good one. Here what have they asked? They have told that in the block diagram above, sustained oscillations occur at its node. So at every node, sustained oscillations occur with H naught equals to 2. So H naught they have given. The op amp has a transfer function now, because if you know, if it's a non-ideal op amp, it will have some frequency response. So if we approximate our op amp as a first order circuit, so the transfer function of the op amp looks something like this, although we approximate it like a second order as well. But if you want to approximate with first order, the transfer function of the op amp will be something like this, and they've given me the H naught value and S and all these things are there. For these oscillations to be sustained, the sign at the terminals A and B must be, what should be the signs at the terminals A and B? So if you see it as everything is symmetric, you will say A and B must be also plus minus. Okay, just everything is symmetric, but it's not the case. What are they exactly asking? Have you understood the question or not? So actually, what does sustained oscillations mean? Sustained oscillations mean if you have ever given an input, and due to that input I am getting my output indefinitely. If you remember control systems, there was one concept known as marginally stable system, where my poles were lying on the imaginary axis. So during marginally stable, my system was neither unstable or neither stable, because it was always oscillating between certain values. So here also the same thing is happening. So to get sustained oscillations, what do I need? So first let's analyze the circuit. So if let's say I'm giving some input here, okay, let's say I'm giving some input, small signal input Vx. So at the output of this particular op amp, what will I get? So for now let's assume A and B as positive. Okay, for now let's assume A and B as positive, A as positive and B as positive. Just hold on. So output will be what? It will be simply Vx times H of S, because it is output of op amp is AD into V plus minus V minus. So this output will be Vx H of S. What about this output? Again, this output will be what? This output will be whatever this was input to the op amp and multiplied by H of S. So this will be Vx into H square of S. Now this is fed into the input of the third op amp. So again it will be multiplied by another H. So this will become V of X into H cube of S. Okay. So initially I gave some Vx, and here this particular op amp is telling me that I should get Vx into H cube of S. For sustained oscillation, if I give some small input, it should keep that input, right? So it should also be equals to, this output should also be equals to Vx. So basically what it means, basically my H cube into S must be equals to 1. Okay. Now as we are concerned with frequency response, because we will mainly provide sinusoidal inputs, I can convert this into H of j omega. h of j omega. H cube of j omega must be 1. Now, it's not only one case that means my magnitude of h cube of j omega must be equals to 1. It's not the only condition. If you remember, if we have studied control systems, then in relative stability as well, we determined few conditions. It was one of the magnitude condition, other one was the angle condition. So here also I will get two conditions. Yeah, h cube of magnitude must be equals to 1. Other condition is angle of h cube also must be equals to 360 degrees or 0. Why 360 or 0? Because this should not have any change in sign, right? If I observe, if this has some change in sign, that means I'm not getting the initial input. It is reducing the initial input. So obviously I will get the same input as provided, as it is equals to 1. So my first, I will go with this plus sign and I will go ahead. If I am wrong, then I will track back and revert my answer. Okay. And then I will verify. So this is my first assumption. So we need to verify these cases. So first I will go with this magnitude condition because they haven't told me at what frequency I am working in. So I have to identify the frequency. So I have told you that what is my h of s? H of s is 2 by 1 plus s 10 raised to power 6. If I want to convert this into frequency response, it will be h of j omega will be 2 by 1 plus j omega 10 raised to power 6. Now, if I want to find out the magnitude of what? H cube of s. So that will be simply magnitude of h cube of j omega. It will be 2 cube divided by 1. For now, I will assume this particular variable as x. Okay, for my simplicity, this as x. It will be x square whole raised to power 3 divided by 2 because I have to do the square root to find the magnitude of this single function and then I will cube it, right? So that's the cube part. And this should be equals to what? This should be equals to 1. So if I equate this thing, this will be 4 equals to 1 plus x square, or x equals to plus minus under root 3. Now obviously I know x is frequency, and frequency we talk about in analog electronics, we talk about positive frequencies. So I will assume x to be positive. I will ignore the negative answer. So my x equals to root 3 plus root 3, or I can say omega equals to root 3 mega radian per second. Okay, as a 10 raised to power 6 was down here. So we got our omega value. So this is the frequency that we are working in. So indirectly they have told us at what frequency we are working in. Now I will determine the phase condition. Both condition must be satisfied. Obviously magnitude needs to be 1 and phase needs to be 360 or 0 degrees. So now if I compute the phase of this h cube of j omega, right? Now the transfer function is simply this, right? Transfer function is simply this, this whole cube. Okay, h cube of j omega is what? H cube of j omega is simply 2 cube 8 divided by 1 plus j omega by 10 raised to power 6, or I can, for now I can simplify this to x, jx whole cube. Now what is the angle of this? So angle due to this plus 8 is simply 0 degrees because it is positive real number, the angle will be 0 degree. Now as the other things are in denominator, I will write negative here, negative. And if you remember that as they are in multiplicative, so I can simply write the power at the front, and this will be tan inverse omega by a, or like imaginary by the real term. So it will be tan inverse x by 1. Now x value I have already found out, that is root 3. So if I put this value here, what will I get? I will get 3 into tan inverse root 3. What is tan inverse root 3? It is simply 60, right? Plus 60. So it will be 3 into 60. I am getting minus 180. So this is not the condition for positive feedback. Okay. For positive feedback, this angle actually should have come 0 degrees or 360 degrees. So my initial assumption was wrong. So let me assume again. So now what I will assume? I will assume that opposite. I will assume the opposite. This will be minus. This will be not this one. This will be minus and this will be plus. Now, if this is minus and this is plus, then output of the op-amp is VD into AD, right? The differential voltage, where positive comes first. So this will be actually negative. So this will become minus Vx h, and this will become minus Vx into h square. This will be minus Vx into h cube. So what I can say, my negative of h cube must be equals to 1, right? Because the transfer function is minus h cube this time. Do remember, please keep this in mind. So my negative of h cube j omega must be equals to 1, or my magnitude of j omega, negative goes away actually if I take the magnitude, should be equals to 1, and the negative of the angle must be equals to 360 degrees. So this condition will be remaining same, right? If this condition is same, whatever we have done the calculation, this will remain same. So our omega will be root 3. Operating frequency will be root 3 mega radian per second. But this will change now. So this will change to what? My minus of h cube of j omega angle should be equals to, like I will calculate this value now. Now what is minus of h cube? So minus of h cube will just be the negative multiplication of this, right? It will be the negative multiplication. If it is negative multiplication, simply I can write 8 by 1 plus jx whole cube, and now we can simply do the calculation that the angle contributed by this is minus 180 because a negative sign is here. So angle contributed by the numerator will be minus 180, and angle contributed by this will be simply minus 3 times tan inverse x, and which is simply 60. So minus 3 times 60 is minus 180. Minus 180 minus 180 gets you minus 360, which is same as 0 degrees or plus 360, right? Or like simple way is, you found out this angle, this was minus 180, so I needed another minus 180 to actually make this plus 180, right? Make this plus 360 or 0 degrees. So simple thing was, you just added a negative sign here. So then and there you proved that okay, I have got negative 180, but I need another 180 degrees to get 360. So I will just change the sign of this, that will give me extra 180 degrees. So like that also you could have done. I have solved extra to explain to all of you. Okay, so I hope you understood this concept, what is the sustained oscillations, and like what is the concept behind it, right? Not just mug up the formula, like you just remember some Berkeley criteria and that's it. So let's move to the next question. So what is this next question telling us? So we have like this configuration op-amp and MOSFET, and they are asking what is the small signal input impedance Zin for the particular circuit. So at first this was DC input impedance, which is incorrect. It should be small signal input impedance. There was some incorrection in the question. So they have given me this AD value, that is the voltage gain of this op-amp, and the bias currents of this MOSFETs, and GM by ID value. Okay, so first, if you are in the examination hall, how you will solve is, obviously if they have mentioned that this op-amp is in saturation because they have told this ID bias and all those things, you can verify as well if the op-amp is really in saturation or not. Okay, then only you will go and proceed with the small signal input impedance. But as this is not your semester examination, this is like some entrance examination. So if they have asked small signal input impedance, that means the MOSFETs will be in small signal, right? Else how will they like ask small signal input impedance? And obviously if it is some sort of NAT type question, then you don't need to check whether the MOSFETs are in saturation or not. So first I will solve, then I will check whether my assumptions were correct, that the MOSFETs are in saturation or not. Those assumptions were correct or not. Okay, so obviously if I take this circuit, take it here, and my assumption is the MOSFETs are in saturation. So if the MOSFETs are in saturation, what will happen is that obviously I want to find out small signal input impedance, right? If I want to find out small signal input impedance, I will connect a voltage source here, V, and I will measure the current I, and the ratio of V over I will give me the input impedance. So and to do that, I obviously nullify all the independent voltage and current sources. So this will be nullified. Okay, this will be nullified, this won't be here, this also will be nullified basically. So if this potential is V, I have a V potential here, and this potential will be what? This potential will be simply AD times V. And what will be this potential? So here, what will be the current through this? So if the VGS, what is the VGS of this MOSFET? The VGS of this MOSFET is simply AD times V. So the current will be GM VGS, right? GM VGS, which in our case is GM AD times V. Now I know the current here, so this one in series, so obviously the current will be same. This same current will flow basically, and I have a current flowing that will be on the upper side as well due to this resistor. So overall I can write down the equations. I can apply a KCL at this node. If I apply KCL, it will be V by 0.32 kilo ohms plus V plus this outgoing current, right? What is this outgoing current? This is GM ADV equals to what? Equals to this incoming current, I current. So from here I will get my V by I ratio. So what will be my V by I ratio? V by I will be simply 1 divided by 1.32, as this is in kilo and this is in milliampere, so I will write everything in their same units. This will be GM times AVD. GM is how much? GM, from here I can find out my GM value. GM value will be 25 millisiemens, correct? So as it is in milli, right? This is also in milli actually, so I will write here milli only. So this will be 25 only, correct? This will be 25 times 15, because AD value is how much? AD is 15, so it will be 25 times 15. This will be my V by I value. So I will just write down the calculation. This will come in kilo ohms. I will later convert it into ohms. So 25 into 15 and plus 0.32 inverse. This will be 1 by 378.125, which will be equals to if I take the inverse and multiply 1000 with it, it will be, okay, this is already in kilo ohms, right? This is already in kilo ohms. Yeah, this is already in kilo ohms. If I multiply 1000, 2.64 ohms. So basically this GM, right, is contributing hugely to reducing the small signal impedance. So your answer will come out to be 2.64 ohms. So yeah, this will be the solution for this particular question. And now if you want to check whether the MOSFETs are actually in saturation or not, so now we'll check. Okay, the solution is done. Now we'll check whether the MOSFETs were actually truly in saturation or not. So how can we check actually? So to check, right, what you can do is first do the given conditions. So obviously we have assumed that op-amp is ideal in the sense that no current goes into the op-amp. Incoming current is 0. So that means what will happen, if this is 1 volt, this has to be also 1 volt. So here I have 1 volt. So what current is flowing through here? Current that will flow through here is 0.8 divided by 0.32. So this will be 2.5 milliamperes, which is exactly equals to the I bias, right? ID bias. So this same 2.5 milliamperes is flowing through this MOSFET and this MOSFET as well, as they're in series. So now as they're in series, now you have identified the current. Now what you can do, you can identify the voltages as well. So I'll just take this thing, the next page I will take. This is the ID bias as given. This was already given, but still I found it out using simple KCL. Now what you want to do is they have already given this as 0.6 volts. This output of the op-amp is 0.6 volts. Okay, so this is 0.6 volts, and I know one equation that ID your GM is equals to 2ID by VGS minus VTH. This we learn when we study MOSFETs. This we learn, right? So from here I can write down my GM by ID is equals to 2 by VGS minus VTH. So GM by ID is what? GM by ID they have already given it as 10 volt inverse, right? And from the units also I can see it is volt inverse units. So this will be 10 equals to 2 divided by VGS minus VTH. VGS I already know. What is VGS? It is 0.6 volts. So your VGS minus VTH is 0.2 volts, or your VTH is actually 0.4 volts, and I will assume both the MOSFETs are symmetrical. Okay, now the first MOSFET is, I have assumed it to be in active region. Okay, So for it to be in like not active saturation region, my VDS must be greater than or equals to VGS minus VTH. Okay, so that means my drain potential has to be greater than or equals to my 0.2 volts, correct? So if this MOSFET is also flowing, like these are a series circuit, right? If this MOSFET, both the MOSFETs are flowing the same current, that means their VGS must also be same. As their VTH is same, their VGS also must be same. So if their VGS is same, the MOSFET M2 has its VG as 0.8. So if VGS is same, this should what should be the VS2? VS2 should be this value, right? This VGS was how much? 0.6. It should be 0.6 down from VG. So here it should be 0.6 down, that is 0.2. What do I mean by this? Let's name this MOSFET as M2, M1. Okay, so I can say VGS 2 should be equals to VGS 1. Why? Because they have same currents, right? If they have same currents, because ID bias is same, they are in series circuit. That means that equation, right? VGS minus VTH whole square, Kn into VGS minus VTH whole square, both should be same as ID is same. So that VGS minus VTH must be same. As VTH is same, that means VGS also should be same. So VGS 1 should be equal to VGS 2. So if I just equate, I know the VG of this, I need to find out the VS2. So here it will be 0.8 minus VS2 equals to VGS1. What is VGS1? VGS1 already I know is 0.6, right? This VGS1 is 0.6. So it will be 0.6. So from here, like I've already found it out, but still for you, I am just solving it further. VS2 will be simply 0.2 volts. Okay. So this point potential is 0.2 volts. If this point potential is 0.2 volts, can I write that thing here? Because my VD1 will be equals to VS2. So VD1 equals to VS2 as they are same nodes only. So I can say this node is 0.2 and which is satisfying the condition. So my VD1 is greater than or equals to 0.2. It is satisfying. So I can say MOSFET is in saturation. Okay, I can safely say MOSFET is in saturation. And here as well, if you want to identify, this potential is 1 volt, right? And if this potential is 1 volt, again my VDS2 must be greater than VGS minus VTH. So my VDS2 is how much? VDS2 is already this is 1, VD is 1 volt and VS2 is VS2 was 0.2 volts, correct? VS2, this was 0.2 volts. We have just found it out. So this must be greater than equals to VGS minus VT. Basically it is 0.2 only. So yes, it is greater than equals to. It is satisfying, right? 0.8 is greater than 0.2. So obviously MOS2 also is in saturation. So from here you can verify that whether they were in saturation or not. Okay, this is not the part of the question. The part of the question was only up until this, and examination hall, if it comes, you will solve obviously up until this, and that's it. But for extra knowledge, you need to understand these things. Actually, what are the like what is happening in the circuit? Are they actually in negative feedback or not? And is this are the MOSFETs in saturation or not? Okay, these things you need to check. So that's it about this question. Let's move on to the next question. So let's start this question. So we will start this question like they have asked the 3 dB bandwidth for the filter transfer function VOS upon VIFS. So we have two op amps and a trans conductance amplifier, right? So it converts voltage into current. Okay. So here it is shown that basically the current will be incoming here GM V0. V0 times the GM, and it will be incoming because negative sign is there, right? That's why incoming. So how do you identify the 3 dB bandwidth? What does mean by 3 dB? 3 dB means I'm 3 dB down from my maximum value, okay, from the peak value. Okay, so if my V of S, not VIFS, sorry, V of S over V of S at DC, because generally what happens at DC I get the maximum gain, okay, will be some frequency A. At DC this will be some gain A. My magnitude at the 3 dB frequency S Vi of S equals to J omega some value, okay, it will be A by under root 2. Okay, that is the main concept behind this 3 dB frequency. It is the 3 dB down from the peak value. Okay, so First of all, I will solve the question and then I will come to the one main thing, that again, how will you understand whether these op amps are in positive feedback or negative feedback? How will you know that? Okay, for now we'll assume both the op amps are in negative feedback, and I will solve the question and then I will tell you how to identify whether these op amps are in negative or positive feedback. Okay, so what I can do is, this current I know is GMVO. Okay, this current is GMVO, and this potential actually I don't know. I don't have any idea over this potential. So what I can do, I can assume this potential as V1 and this potential as, okay, as this is in negative feedback and this is ideal op amp, so VGC will be applicable. So this node potential will be simply 0 volts, right? Because this potential is 0, so this potential also will be simply 0 volts. So I can assume this voltage to be some voltage V. Okay, so I can apply a KCL here and a KCL here as well. Okay, that will help me to do all the computations. So if I apply a KCL at this node, I will get what? It will be VI, not VI, sorry, 0 minus VI divided by 1 kilo. Now I will assume all the currents to be in milliamperes, and okay, this is 1 kilo plus 0 minus V divided by 1 by CS. I will not write the capacitance value for now. And the other node current is how much? This node current is GM times VO, right? GM is not mentioned here. Okay, GM, actually I missed the value of GM. I will quickly see from the question what was the value of GM and then I will put it. Yeah, GM value is this 1 milliamp per volt. So I just forgot to write that down. Apologies for that. So it will be GM. I will assume current is in milliampere. So this will be only 1 into VO. And that's it, right? Because there are three currents that are going out. One is this, other one is this, the third one is this. Inside the op amp, no current is going, right? So this is one of the equations. And now what I will do is I will copy this particular thing, take it to the next page. What about the other equation? So other equation will be this, right? KCL at this node. So again it will be 0 minus V divided by 2 kilo plus 0 minus VO divided by 4 kilo plus yeah, these two nodes are only there, right? This third node is current going is 0. So I can replace here my VO. So what will be my VO? VO will be minus 2V, or other way around I can write V will be equals to minus VO by 2. So here I can write this will be minus VI. I am writing this in milliamps only, plus this is minus, this will be V naught divided by 2 into C into S, right? So what I will do, actually this is in milliamperes format, right? So I want to write the capacitance directly here, 10 pico only. So I will assume my frequency S to be in gigaradians per second. So S is in gigaradians per second. Okay, that is my assumption. So I can directly write here the value of C. Value of C is simply 10 pico, right? Just this whole term should be in milliamperes, because if this V by sorry, this was VI, right? This is V. This VI by 1K, right? It is in milliamperes. That's why I am converting all the units into milliamperes. So this is S, and this is what? Just hold on. This is here plus VO equals to 0. So now I can write my VI over VOs. V of S. VO over VI is how much? So if I take the VI that side, this will become, this is 5. So this will be 1 by 1 plus 5S. Okay. So now what I wanted to compute. So I wanted to compute basically that what is the 3 dB frequency, right? How do I compute 3 dB frequency? The magnitude must be what? The magnitude must be under root 1 by 2. So if I want to compute the 3 dB frequency, V over Vi, because at S equals to 0, the gain is 1. So at S equals to J omega, the gain should be 1 by under root 2, so which is equals to 1 by 1 plus 25 omega square whole under root. This should be equals to 1 by under root 2. So from here I can easily find out my omega. So my omega is how much? Omega will be, I'll just quickly compute this. It will be 1 by 5. Okay, or 0.2. What is the unit? Unit I have already assumed it to be gigaradian per second. 0.2 gigaradian per second. But in the question they have asked in mega radian per second, right? Mega radian per second. Okay, they have not asked any units. So basically it will be equals to, in mega radian per second, if I write, this will be 200 mega radian per second. Okay, this will be the answer for this question. Now, how do you actually write this thing? How do you actually understand that this is in negative feedback? So you can understand each block in isolation. So first, if I want to only take this first block, right? If I want to only take this first block, so if I just again use the same principle, that I will cut this one off and I will increase some voltage here, delta V. Okay, if I increase some voltage delta V, what will happen? This GMVO current will actually increase, because VO is delta V only, so this will increase. So this will increase. So here more current will flow out. Now if more current flows out, more current flows through here. So this potential actually increases. This node potential reduces, right? As more current is coming out, this node potential will obviously reduce. Why? Because this voltage drop is increasing, but this is plus minus. So if I am calculating voltage here, it is actually net reducing. So this voltage is actually reducing. Now if this voltage is reducing, that means it is, like, I will assume this op-amp to be negative feedback, or if you want to assume this as open loop system as well, that also you can assume. So as there is a negative sign, this will simply flip the change, so it will increase the voltage. Here this voltage is increasing, so hence this voltage will also increase, right? This voltage will simply increase. If this voltage is increasing, and this is just an open loop system, so if this is an open loop system, what will happen? The negative terminal of a op-amp voltage is increasing, that means overall output will reduce, which is opposite to my initial sign. So obviously this op-amp is in negative feedback. The same principle you can apply for this op-amp as well, and you will get back the same result. Okay, so as this lecture is very increasing in time, so I don't have enough time to spend over explanation. So that's it basically for this amazing session of op-amps. I hope you enjoyed it. I hope you learned a lot of new concepts, and in the next part I will solve interesting questions on MOSFET. And please do watch the other videos as well. And also, if you are interested, you can go and check out our website in preffusion.in, where we have launched full courses for VLSI campus placements, and as well as gate course full courses. You can go check out our website preffusion.in. Until then, happy learning and thank you for watching.